Okay, so what we called cover the RAID controller, and we meant by RAID redundant array of inexpensive disks, and some others like called independent disks. In another sense, I will use multiple smaller disks instead of just one large disk. So I can do, as an example, parallelisms, and by doing parallelisms, I will improve, of course, the performance. I can have like some extra disks for redundant data storage. And this is, as we will see, it will provide fault-tolerant storage system, especially if failed disks can be hot swapped. So what does that exactly mean? Meaning that assuming that you are working in a company or in the IT of the company, and the company like has a server, and the server has only one disk. Hard disk one hard disk. What do you expect if this hard disk fails? The whole company will drop, so we can't send an email, whatever like saved is gone, all of the files is gone, and so on and so forth. And of course, if you are the responsible for that, you will get fired the next day. Correct? So we have to do something. We have to think of something that to save us the data in case there is a failure, correct? And this is what we will cover. There are like types of ways that we can use in order to enhance the performance and to decrease the failure rate. Okay? First of all, there is something called RAID level 0 or RAID 0. What's exactly RAID 0? So I don't have any redundancy at all. I have the disks, just stripe the data over multiple disks. That's it. So in order like to make sure that you will understand all of these, so let's do it one by one. So first, RAID 0 or level 0. In this one, multiple smaller disks, meaning that I will have my disks here, and I will just do the striping. I will spread the information over the 4 disks, meaning that if I have like sector 1 as an example, I will write sector 1 byte 0 here. I will write sector 1 byte 1 here. I will write sector 1 byte 2 here. I will write sector 1 byte 3 here as an example. So I'm striping the bytes that I have. So instead of putting like sector 1 all here, sector 2 all here, sector 3 all here, sector 4 all here, I'll just do the striping like that. But what will be the benefit? Still, if one of these fail, I fail. Correct? What will be the benefit in your opinion? The benefit of this is increasing the performance. It's not the failure rate, but increasing the performance, meaning that I now can parallel write and parallel read. So if I would like to read from sector 1, I can parallel read of these bytes and parallel writes. Correct? So now I'm increasing the performance. So I can do this faster. Correct? But in terms of failure, unfortunately, I didn't enhance anything, because if any of these disks fail, I fail. Correct? But writing in parallel, reading in parallel, it will increase the performance. So it's basically, with this one, we are spreading the sector over multiple disks. And striping means multiple blocks can be accessed in parallel, which increase the performance. Okay, so this is our first option. Second option, RAID 1 or level 1. How we will do level 1? It's basically, we do redundancy. Via mirroring. Meaning that if I have 4 disks, I will have another 4 disks. So if this is disk 1, this is disk 2, this is disk 3, this is disk 4. So this will be the mirror of 1, this will be the mirror of 2, this will be the mirror of 3, this will be the mirror of 4. And I don't do any striping. It's just mirroring. So if one of these fails, I have the backup. But the problem here, that if I have 2 failures with the same exact disk, meaning that if I have this fail, and if I have this fail, what I will do? Unfortunately, I fail. With this example, unfortunately, I fail. But if this fail, and this fail, then I have no problem. Correct? Because if this fail, I have the backup. I have the backup here. If this fail, I have the backup here. So there is no problem with this one. But I don't do any striping. So I'm not like basically spreading the data over the disks. So they said that, okay, with this one, you get high performance. With this one, you get redundancy. Can we do both? Meaning, can I have redundancy and in the same time increase the performance? Because unfortunately with this, I can't read in parallel. But I have redundancy. So can we do both? They said, yeah, that's fine. You just like have another one that is called read level 0 and 1, which you are combining these two ideas together. Meaning that in this read level 0 plus 1, you will have both. So you have mirroring, but also you have striping. So here, byte 1, byte 2, byte 0, byte 1, byte 2, byte 3, and the same here. So now you are increasing the performance, and at the same time you have redundancy. And people said like, okay, so that's very good because now I have 2 in 1. I have the highest performance, I have the redundancy, so if anything things fail, I still have a backup. And this should satisfy us. But unfortunately, there is a drawback here. In addition, of course, if this is and this is failed, there is another drawback. Money. So if you have 100 disks, should you mirror it but another 100 disks? And this is something usual if you have like a university as an example. Yes? If you have thousands of these, you have to mirror with another 1,000. And the space. So it's money and the space. Correct? So how we can solve that issue? They said, okay, let's go to another thing called read level 2. And in read level 2 or read 2, they said like, okay, so we will also have redundancy, but not via memory, via mirroring. It is via ECC, error correcting code. Error correcting code. What does it mean? Meaning that with this read 2, we will have it like that. So I have my 4 disks, and then I will do redundancy, but instead of 4, I will do 3. How I can calculate the number of redundant disks? It will be satisfying this formula. The number of redundant disks is equal to log to the base 2, or it will be 1 plus 1 plus log to the base 2 of the total number of data disks. Let's apply this here. The number of redundant disks will be equal to 1 plus log 2 to 4. It's 1 plus 2, it is equal to 3. And that's why I have here 3. With this, I am decreasing the number of redundancy. And of course, if this increase, this will not be exactly the same. So if I have 5, I will not have 5. It will be again with the same things, and so on and so forth. Okay. But how this will work? We would like to know how this exactly will work. So this is, we'll do like with the same idea, like with the parallel writing, sector byte 0, sector byte 1. Byte 0, byte 1, byte 2, byte 3. And we will have something called even parity, as we will see right now. If I will call this disk number 3, if I will call this disk number 5, if I will call this disk number 6, and I will call this disk number 7 as an example. This guy will check the disks as follow: 4, 5, 6, and 7. And this guy will check 2, 3, 6, 7. And this guy will check 1, 3, 5, 7. 1, 3, 5, 7. What does that mean? Meaning I will check these number of disks if they have even parity or not. What does it mean by even parity? Since I'm writing the bytes, yes, in parallel, I will check, as an example, if I have 4, 5, 6, 7, if they have even number of ones or not. If they don't, so this means that there is an error. If they do, so this means that everything is correct. Let's see. Assuming right now that I have here 1, I have here 0, I have here 1, I have here 0. And this disk called 4, and this disk called 2, and this disk called 1. I will go to 4, 5, and 6, and 7 and see like how exactly should be what I need to write in this disk. If I go to 5 and 6 and 7, 5 is here, 6 is here, 7 is here. 0, 1, 0. How many ones do I have? I have only 1, correct? If this is an even or odd number. Odd number, correct? But I'm telling you that I'm checking the even parity. So this means that I have to add a 1 here. So if I include 4, 7, 6, 5, I have 2 ones, or even number of ones. So if I will go with this check, 4, 5, and 6, and 7, 1, 0, 1, 0, I will find that I have even number of ones. How about this guy? By the way, for the quiz, I will expect that you will be familiar with what I am explaining right now. Let's check this guy. 2, 3, 6, 7. I have the 2 here. 3, 6, 7. Where is 3, 6, 7? 3, 6, 7. 1, 1, 0. How many ones? 2. Is this even or odd? Even. So should I add any ones in this? No, because it's already even, so it will be 0. Is this clear? How about this guy? 1, 3, 5, 7. So this is the 1. Where is the 3, 5, 7? 3, 5, 7. 1, 0, 0. How many ones? 1. Is it odd and even? Odd. Should I add another 1 to be even? Yes. This is if I am calculating an even parity. And by default, with this, we will calculate the even parity. But if I'm asking you, like, calculate odd parity, so you will do something the same, but just you need to calculate the number of, or you should ensure that the number of ones should be odd, if it is odd parity. If it is even parity, the number of ones should be even. So one can say, like, okay, we did understand what you have explained right now. But can you just, like, elaborate more or explain more how this will pick up the error? Meaning, if I have an error in any of these data disks, how I will be able to know? Let's take an example. Assuming that for some reason this one with a mistake went to 0. How we will be able to catch that error? Let's go to check 4, 5, 6, 7. 4, 5, 6, 7. Calculate the number of ones. 1, 0, 0, 0. So the number of ones are odd, which is not correct. Yes? Yes? So I know now that I might have a problem in any of these disks. Correct? It can be either 4 or 5 or 6 or 7. Let's go to the next disk. This next disk, check 2, 3, 6, 7. 2, 3, 6, 7. 0, 0, 0, 1. How many? Odd. Is this correct? Not correct, yeah? So this means that I have in 2 and 3 and 6 and 7, and here 4, 5, and 6 and 7, the two common is 6 and 7, correct? So for sure now it is in 6 or 7. I have excluded the others, yes? Because a mistake happened here, and 6 and 7 are common here and here, so I'm sure now that it is either 6 or 7, correct? So now I know that it's either this, 6 or 7. Let's go to the third one. 1, 3, 5, 7. 1, 3, 5, 7. The one has 1, 0, 0, 1. So it is correct. Even parity, correct? If it is even parity and the 7 here, so this means that the error in 6, yes? So I have captured the error. And if I have captured the error that this 6 is 0, that's an error, so of course I should remove it, and I should send it back to 1. So I have been able by this system just like to detect the error and to correct. Yes? But just one error. If I have multiple errors with this system, I won't be able to capture. But if I have one error in my data disk, I will be able to capture by this idea. Okay. And the nice thing also about this guy, that assuming that I have a failure on this disk, boom, I lost that disk. Did I lose the whole information? I can just like plug another disk, and by doing all of these, it will be able to restore all of the data in that particular disk. Correct? And this is what we call it in the companies, or even like in the science, hot swap. That you have a failure in one of the disks, while the computer is on, you can remove that disk and plug a new disk. Hot swap. So you can swap while it is on. And that disk, the new disk, will restore all of the data in that failure disk without having to shut out the system, without having any complaints from the employee, managers, and nothing. So you will be happy, the employee will be happy, the manager will be happy. And usually when you do an installation with the servers and so on, you have like the options, which one you will choose. And according to which one you will choose, of course, now you know how the calculation should be. You should know like how many disks you should include. Okay? Then designer said like, okay, we need even better. So we understood right now that we have all of these error correcting cause. We have decreased a little bit instead of mirroring with applying this formula with log to the base 2. We are decreasing the number of redundancy, but we need things better. They said, okay, that's fine. We will have another thing which called red level 3. In this red level 3, we call it bit interleaved parity. And then this guy, he will have also the 4 disks, but they will have only one redundant disk. Only. And then, in order to calculate the parity here, they will take this, and this. They will XOR and write the data here. And with this, they can either choose also the odd parity or the even parity. But they will have only one disks for parity bits. And the number of redundant disks will be equal to 1 plus the number of protection groups. So as an example, if I am doing odd parity, and this is 1, 0, 1, 0, so here is even, I will add 1 here in order to be odd, as an example. But then they said, okay, that's fine, but now we have only one parity. How we will be able to check where is the error? How? You understand my question? So now I have one parity, yes? So if I have an error in this one, so this is 1. So 1, 1, 1, 1, they are even. Oh, so I know now that there is an error, but where? They said we will add another thing. So we will do checksum for each disk, which will tell us which disk has the error. And then if we know that that disk has an error, and then we will do the parity, we know that exactly where is the byte or the bit that has the problem, and then we will correct it. Meaning that with each of these disks, we will have here the checksum. The same will happen with the second, the same will happen with the third, and so on and so forth. With this checksum, it will tell me that this guy has the problem. It will do the checksum for all of the bytes here, and it will tell like, hey, there is a failure here. But how I will know if the failure in the first byte or the second or the third or the fourth or whatever it is, I will know that by doing this and this and this and this parity, and then I will know that that particular guy has the problem, or I will correct it. So with the checksum, I will know exactly which disk. By the parity, I will be able to correct what is the data that is there. Okay? Or which bit exactly has the error. Did you get that? Question. Then they said like, okay, we don't want to distribute the bits, we would like to distribute the blocks instead. And that's why now we will have something called RAID 4. With this RAID 4, distribute the blocks instead of bits. So now I will have again my 4 data, and then I will have an extra one, but this as an example will have the first block, second, third, and fourth. And again, this what we call block parity disk. And in order like to get a new one, I will, so if I have like as an example another redundant, another disk here like that, so what I will do is I will take whatever I have with the old one, or sorry, with the new one, and then with this parity and with this guy, and then I will calculate the new parity, which gives me an indication that I don't have to include all of these while calculating the parity, as an example with this one. I will show the difference in a second when I go to the slides between the level 3 and the level 4 and what is the benefit of level 4. Then they said, okay, so that's fine, but the problem that we are facing right now, that we always, you just said that I can calculate the parity for this guy just by this and with the new disk, and I don't need that. However, you said that you always take this disk as a parity. So this means that you can't do parallel write and parallel read, because you always have to use that parity disk. And also if this fails, boom, all of things fail. Then they said like, okay, we will go to RAID 5 when we will distribute the parity. So the parity not always here, the parity might be here, the parity then might be here, the parity might be here, and so on and so forth, as we will see in the slides. So going back to the slide, I have already explained the RAID 1 and RAID 2, RAID 1 by mirroring, RAID 2 by error correcting code, RAID 3, which is basically bit interleaved parity, and we have explained, and with RAID 4 we just have an n plus 1 disks, and we have the blocks instead of the bits. And here is the difference between RAID 3 and RAID 4. With RAID 3, as we mentioned, so if I have a new data to be written as an example in D0, I will take this data with D1, with D2, with D3, do XOR, and then calculate the new parity. And then I have now the new data written here. But with RAID 4, I don't have to include all of the disks. If I have a new data that need to be written in D0, what I will do, I will take the old value, just the new value, XORed with the parity, and then I will calculate the new parity. What is the benefit of that? That I don't need to include that other disks while calculating the parity of this new stuff. What is the benefit of that? The benefit of that I don't always need to check the whole disks. Yes? So I'm increasing the performance. And the other thing that you will see right now, that by doing that, I can do the idea of level 5, which I will introduce right now. So with RAID 5, right now, I can distribute my parity. With this guy is RAID 4, this guy is RAID 5. With RAID 4, as we mentioned, we have the parity all in one disk. So if I would like to write this data here, I have to calculate it with this parity to write the new parity. If I would like to do this, I have to do this with this parity to calculate, with this parity to calculate the new parity, and so on. So I have to access the disk always. So I can't do parallel writing and parallel reading. But with this RAID 5, when I distribute the parity over the whole disks, I can do that. Why? Because if I would like to write a new data for this 0 as an example, so I'll take this 0 with this parity and then calculate the new parity. And as an example, if I would like to calculate something for the 9, then what I will do is I will calculate it with this parity, which is another disk, to write the new parity, and so on and so forth. So can actually do multiple write and the multiple read at the same time, because the parity are not exactly in only one disk, they are distributed. This is the first benefit. But the second benefit also, that I don't have a bottleneck right there. If this lost, I already lost everything. If with the distributing parity, I don't have the same exact thing. So by doing, so with now I finalized the options or the red types that we have right now. So it can improve the performance and availability. Assumes, of course, independent disk failures. Unfortunately, it will be too bad if this happens. No one will be able to save you, unfortunately. There's also input-output performance measures. So input-output bandwidth, which is basically the throughput, and all of you know exactly what is the definition of that, the amount of data that can be written or input and output and communicated across an interconnection. But now, as you can see, input-output performance. Yes, it's not memory performance, input-output performance. So this will be, the data will go from the memory to the input-output and back again. Yes. So now I'm interfacing with outside the computer, correct? Just like any device, any input-output device. So if, as an example, I'm communicating with the keyboard, this is called an input-output. If I'm calculating with the printer, this is input-output, and so on and so forth. So how much data can we move through the system in a certain time, and how many input-output operation can we do per unit time? Input-output response time, which is basically the latency. And you already also know that, as we have explained earlier, but this will be applied into the input-output instead. The total elapsed time to accomplish an input or output operation. Yes, it's just like how much you will take in order like to get the job for me. So this is basically the latency, or the input-output response time. So many applications, of course, will require both high throughput and short response time. So these input-output systems, we have something called bus, which will interconnect the systems with our computer, which is a shared communication link that needs to support a range of devices with widely varying latencies. So now with this bus, I will have all of the connection shared. I will have the connection to the, as an example, printer, connection to the keyboard, connection to the mouse. Any connection to the input-output will be directed, will be connected to me, which as a computer, through that bus. So if that guy would like to speak to me, speak through that bus, send the data, and then it will come to me. If the other one would like to talk to me, also it will send to the same bus, and then will connect to me, and so on and so forth. So what is the advantage? And what is the advantage and disadvantage of something like that? The advantage, of course, that this is something cheap. Yes, I don't have to do a set of connection between each of the nodes and myself. Yes, I have just a bus that will connect all of the system. Or versatile, like new devices can be added easily. I don't have to remove anything. I don't have to add a connection. I don't have to do nothing. It's just like connections, and that's it. But what would be the disadvantage of something like that? And of course, it will be cheap, because now I don't have to do as many connections as needed. It's just like one connection. I will be able to easily plug and play. But what will be the disadvantage? Disadvantage, as you can see here, is the communication bottleneck. Why? What does it mean here? Bus bandwidth limits the maximum input-output throughput. So as an example, if I have a connection which can transfer 100 megabytes per second, as an example, but your input-output can do 1,000, will I be able to do a 1,000 megabyte per second as between me and the device? So as a computer, I can do that. As a device, I can do that, the 1,000 megabyte per second. But the connection can't do that. The connection can do 100 megabyte per second. What do you think will be the performance? Lower performance. Why? Because of the bandwidth of the bus itself. And this is, by the way, it's one of the extremely important problem that we are facing, or in industry, or the basically the companies are facing. is the buses. It limits the performance a lot. So that device can work with high throughput. The computer can work with high throughput, but unfortunately the bus is a big problem. I can't do that like very high throughput. So there are benefits of that. There's just like plug and play as that they mentioned, low cost and versatile, but unfortunately it will limit the throughput. Because usually with the buses, like there are limits for that, and there are a lot of reasons. I don't want to go to that, but it is covered more in a network class. But at the end, it will limit the performance a lot, unfortunately. There will be a lot of crosstalk between the connections. There will be like, if I would like to do something very high, this means that it will consume a lot of money and a lot of power and so on and so forth. And there are also a lot of other limitations that even I cannot do. So if I will have the heat sinks and if I will have all of the money, still are a lot of limitations that I cannot do better than that. And unfortunately, the bus will limit my connections or my bandwidth at the end. So the maximum bus speed will be limited by the length and the number of devices that I can have on the bus. Type of buses. So I might have a bus between the processor and memory, and usually this is very short, but would have a high speed. I have an input-output bus, as an example, USB or SCSI or something like any standard industry bus. This is usually lengthy and slower, and of course need to accommodate a wide range of input-output devices. The backplane bus, like ATA, PCI Express, and this is basically allow all to work together. So I will allow the processor with the memory, with the input-output device to coexist on a single bus. I'm not expecting, by the way, that you will remember these details, but of course I am expecting that you will be familiar with that, yes? This, we have like 3 types. What will limit that, the length, and so on. How many devices are in the systems. With this input-output transactions, so an input-output transaction is basically a sequence of operations over the interconnect that include a request and may include a response, either of which may carry data. The most important thing that I would like you to be familiar with, that if I have any input-output transaction, it includes 2 parts. How? So if I would like to communicate with you, how we will communicate? We will be communicated through like 2 parts. First, I have to send you what is the address that I need. Correct? I send you the address, and then we'll begin to receive or send the data. So I can send you the address, and then after that we will have the data. Because unfortunately, I have to ask you for something, yes? I have to ask you that I need something, or I have to ask you that I am sending something. And in either or, I have to give you first the address. Correct? And also, the bus transactions are defined by what they do to memory. So if I said, like, as an example, a read transaction reads data from memory, if this is input or output. I'm saying here what they do to the memory. Read. Or write transactions, write data to the memory. So if this is input or output. Again, read transactions, read data from memory. So I am going from the memory, output or input. We are describing what they do to the memory. Is this read, and this is the memory, I am reading from the memory. Is it output or input? Output. Yes? I'm reading from the memory, so I'm going output. Write transaction, write data to the memory. So if I write to the memory, so this I will call that this is input. Yes, so if I'm sending an address and I'm sending to you data to the memory, so this will be an input, yes? If I'm reading from the memory, I send you an address and then reading from the memory, so this means that I'm an output. We call it input-output device, correct? But what exactly will be the input is what exactly I'm interfacing with the memory. Do I write or read from the memory, and then I will be either an input or an output. Also with the bus types, I might have asynchronous or asynchronous. What are the difference, or the main difference between synchronous and asynchronous?
Synchronous is with the clock signal, and asynchronous is without a clock signal.
So basically, if there is a clock signal, it will be synchronous. If there is no clock, so this means that it will be asynchronous. Meaning that if I have a clock that will determine exactly how I will speak to you, so this means that I'm speaking synchronously. Yes, there is, as an example, timer or a clock with the seconds, and with each seconds I have to send the data. I have to send a certain data. With each second I have to send a certain data, and so on and so forth. If there is no clock, it will be asynchronous, and we will see the details of how I can interface in asynchronous between two buses, as we will explain shortly. So if we see like the fire wire or the USB. The USB, for your reference, it is synchronous. The fire wire will be asynchronous. Types, of course, both are input-outputs. Maximum number of devices, I can have here approximately 63. This is 127. Maximum length, this is approximately, both of them are the same. Peak bandwidth, this can go for 50 megabit per second, megabyte per second, and this can go to the, even with the high, with the 60 megabytes per second. So with this synchronous bus, of course, it will includes a clock in the control lines. Advantage, it will involve very little logic, and it can run very fast. So I have a clock, I will run with whatever like the clock rate. I don't have like to have a lot of logic to do that, as we will see the difference with the asynchronous. Disadvantage, unfortunately, all the devices that is in that particular bus, they have to use the same exact clock rate. So if I have, as an example, a slow clock rate, and I have like another device that can work with higher rate, it will just stick with whatever I have. Also, to avoid clock skew, they can't be long if they are very fast. What is a clock skew? So as an example, if I am here at that my location, and then I am assuming that now this sound wave is traveling, yes? Of course, it will arrive to the first row faster than it will arrive to the last row, correct? However, in my expectation, I'm assuming that it will arrive the first row exactly the same time that will arrive the last row, correct? This is my assumption. But the real situation is not like that, yes? And then I might have, instead of clock skew, sound skew, meaning that it doesn't exactly arrive to all of the nodes the same time. So if I have a closed node, it will arrive, as an example, maybe after 1 microsecond. But if I have a very far node, it will arrive maybe after 1 microsecond plus a couple of nanoseconds. Okay? And if I have a very fast clock, this will make a problem. And that's why I have to take care of something like that when I'm designing my circuit. So if I have the CPU and any nodes that interface with that, if it's too far and I have a very high clock, then might be a problem. And that's why this is also another limitation with the high clock rate. Because if I will go to the gig, yes, so the nanoseconds will make a difference. If I go to gigahertz, the nanoseconds will make a difference. correct? Because this gig is multiplied by 10 to the power 9, yes? And the nanoseconds is 10 to the power of minus 9. So with the gigahertz, the nanoseconds will make a difference. So if I have a clock skew, meaning I will assume, as an example, that the clock arrived to that particular node, but it didn't, then of course I will have errors. With asynchronous bus, so there is no clock, it is not clocked at all, it will require a handshaking protocol. So with this asynchronous, I have to send like a request, and then you say like hi, and then we handshake, correct? And then like bye-bye, bye-bye. Yes, this is basic asynchronous. There is no clock that will control the interface between me and the device. So basically, we are controlling the interface between each other. There is no clock that say like, hey, as soon as this clock begin, I can speak to you and you can speak to me. And then when it stop, then it stop. No, it's not working like that. It's basically handshaking. So I will have additional control lines, as an example, read, request, acknowledge, data ready, and so on and so forth. So what will be the advantage? I can accommodate, as an example, a wide range of devices and device speeds, because now they don't belong to the same clock. So this one, I can speak with it with like higher performance or higher bandwidth. The other one can speak with like lower bandwidth and so on and so forth. Can be also lengthened without any worrying about the clock skew, because now we don't have a clock, so I don't have to worry about the clock skew, so I can make like even more lengthy. But the disadvantage, unfortunately, it is much slower. So we need to see an example of how I will get the hand shaking, meaning how the input-output device will interface with the memory, which of course will interface with the CPU. How exactly this handshaking will take place? Will I say just hi and say bye and then that's it? How I will send the information, how I will receive the information, how the memory will understand that I have sent something, and how I will know that the memory received whatever I have sent, and so on and so forth. So please concentrate, because I will go with a step-by-step on this diagram, okay? And I will assume that you will be familiar with something like that. At the very beginning, the input-output will send a read request. And when I send a read request, so that meaning that I would like to read something from you. Me will be the printer or whatever, like the thing that I have, or mouse, or keyboard. I would like to read something from you. But I have to tell you exactly what is the address, correct? So as soon as I'm sending a read request, I have to let you know exactly what is the address of the something that I need. So I have through this to the bus. I have sent a request. I have sent the address. Then I will listen. Did the memory get that or not? If the memory get that, it will send an acknowledge. And I will hear that there's an acknowledge. And I will understand that the memory now received my read request and my address. As soon as I know that the memory received everything that I need, I will just return back my read request to 0. So I will release it. And I don't have, of course, to have the address no more. When the memory will understand or will see that I have released the read request, it will also release the acknowledge. But then what will happen? So I'm requesting something from you, and you told me, yes, yes, I hear it. Then, what you need to do? Send me these things, yes? This is what I request. I request from you something, and you return it back to me that, yes, I know now what you need. What I'm expecting from you next is what? To begin to send that whatever I need, correct? And this is what the memory will do. We'll send the data in the data bus, and will tell you in a signal that the data is ready. When you see that the data is ready and the data in the bus, you as an input-output will send an acknowledge. When you send an acknowledge, the memory will understand that you have already the data. And when you have already the data, so it will release the data ready and the data. When the input-output will see that you have already released the data ready, it will release also the acknowledge. This is what we call with handshaking. Can you see like all of these steps? And of course, if I have all of these steps, I have to have implementation-wise devices that can basically take care of all of these, that it will check, it will send, and so on and so forth. Again, I will go over this one more time. At the very beginning, the memory will see the read. Of course, I will send the read request at the very beginning with the address, but the memory will see that and it will send an acknowledge or raise the acknowledge. The input-output device will see that particular acknowledge, and then it will release the read request. If the memory will see the releasing of read request, it will also release the acknowledge. Then the memory will send a data ready and will send the data on the bus. And then after that, the input-output will see the data ready and the data, and then will send an acknowledge. And then if it will see that, it will release the data ready, and it will just stop the data. And then the input-output device will see that the data ready goes low. It will just drop the acknowledge. So exactly if I'm speaking to you and you are so far, yes? So we have to have a sign, yes? So I have sent you that, and then you have to say like, I receive it. And then like after you receive it, you have to send back to me whatever I need. And when you send back whatever I need, after I receive it, I have to tell you that I have received it. Otherwise, you have to resend it again. If things will be more complicated than that, so as an example, you didn't see the acknowledge. What you will do? I am an input-output device. I have sent the data, and there is no acknowledge. What do you expect I should do? Send it again. Yes, I will send it again. And of course, there should be a protocol or a protocol that all of my network need to follow. It's exactly the same as I mentioned here in our class. We have a protocol. So if someone speak, if any of our nodes speak, all of the other nodes need to listen, and we have to follow that particular protocol. Also with this, if I would like to request something from you, you have to acknowledge. If not, I need to keep sending. According, of course, like to the network protocol, you might keep sending maybe 3 or 4 times, and then you stop to give the turn to another node, and so on and so forth. There might be a failure on that particular connection. And also the other way around. So if I'm sending you the request, and you have received it, and then you have to send an acknowledge. When you send an acknowledge, what I expect next is just to fulfill whatever I have requested from you, correct? So I have requested this particular data. So what I'm expecting that you will send that particular data, and so on and so forth. And also when I receive that data, you need to know that I have received. Otherwise, what you will do? Resend it again. Yes, I have requested from you something, and then you just like respond, hey, here it is. I have to say like, thank you. Yes? You should know at that time that I have received the requested data, and so on and so forth. Any questions? So with this, we call it like hand shaking. So we have here the hand shaking. We have here the hand shaking. So these are typical input-output systems. So we'll have like, as an example, the memory controller. We will have the input-output controller. So I might have like the disks connects to the input-output controller, the keyboard or the mouse or the USB, all of these PCI Express and so on and so forth. Here you will have like your processor that interface with the memory. I'm not expecting that you remember exactly what is there, but just like also understanding how exactly things are there. So with this SPEM, I might have like a MIPS processor simulators, which can support one memory mapped input-output device, a terminal with 2 independent units. I might have a transmitters right